And we're back. Okay, now we're on day 3. We're going to roll through these pretty quick also, if we can. Magnesium and aluminum are in the same period of the periodic table. It doesn't matter which two elements they are, okay? The key in this problem is that they're in the same period, which means the same horizontal row. Consider the following features of a magnesium atom and an aluminum atom. The total number of shells that contain electrons, okay, that's definitely going to be true. All right, but in the same period, they have the same number of shells, right? Basically, the first period is one shell, the second period is a second shell, so on and so forth. Number 2, the shells that holds the bonding electrons. That is also true, okay? Because it's the last energy level, okay, that the bonding electrons are contained in, okay? The highest numbered shell, if you will, all right? And then 3, the number of bonding electrons. That is not true, okay? If bonding electrons are true, they have to be in the same column or group or family, okay? Vertical columns, like over here, are called groups or families. All right. Horizontal rows are called periods. Okay. So what is true? Wait, which of these features is the same for the two atoms? Okay, 1 and 3 are true. So 1 and 3 only, or sorry, 1 and 2 only, not 3. Let's see. Okay. The first two are true. The number of bonding electrons is not. It have to be in the same vertical column. All right. Consider the group highlighted in the image of the periodic table below. This was hard to see. I apologize. I answered that for you so you guys could know which one it was. That group right there are the alkaline earth metals. Da-dum-da-dum, D. Okay? A would be the alkali metals. Transition metals are here, right? Group C through 12. And the intertransition metals are the bottom two rows, all right, which fit in right in there. All right. Diamond and graphite are forms of carbon. On a Mohs scale of relative hardness, diamond is much harder than graphite, right? This is a graphite pencil. I can write with it. Diamond I can't write with. It's very hard, okay? I might etch glass with it, but I can't write with it like I can this, okay? Graphite's very soft. Diamond's very hard. These are allotropes of carbon, very common ones. All right, that's day 3, or part 1. Here's day 3, part 2. Okay, use the information provided to answer questions 36 and 37. The locations of 3 elements are numbered in the image of the periodic table below. Here's number 1, 2, and 3. That's actually aluminum right there, and then we go over from there. All right, none of these 3 elements is classified as a what? Metal? Well, number 1 is actually metal. Number 2 is a metalloid. And number 3 is actually non-metal. D, noble gases. The noble gases are over here. None of those are noble gases, right? D's the answer. All right, what types of elements are the ones whose locations are numbered 1 and 3 respectively? Well, that's going to be a metal for number 1 and a non-metal for number 3, okay? So that would be B. All right. Now, you might say, well, how the heck am I supposed to remember that, Mr. Holmes? All right, go back and watch the video where I went through and labeled all these things on a periodic table, right? It's in your thing. But basically, if you start at this corner right here, okay, I'm going to shade that guy in, and I'm going to go down this diagonal, shading in. Those are all metalloids, okay? And then skip that one where the number 1 is. That is aluminum, and it is metal. But then shade the next diagonal, okay? Those are also metalloids. All right, that's a quick refresher for you. All right, guys, this was in the notes. This is a blank periodic table. I can't really see all of it here, okay? We labeled this in a video. I highly recommend you watch that video, okay? I'm not going to go back and label everything again. All right, that's the end of day 3. Now let's move on to day 4. Okay, day 4, this is Q2. All right, I'm going through the answers for you. We're going to try to roll through these really fast. All right, which of the following occurrences best represents a physical change? Physical changes are best described as a change in state, maybe a change in size, right? But it's not changing to a different substance. If you change to a different substance, that is a chemical change. All right, popping corn kernels in a microwave oven, softening of butter when taken out of a microwave and left in a warm spot, that is definitely going to be a physical change. So let's go with B. All right. Caramelization of sugar using the flame of a torch, you're actually cooking the sugar and you're making something different, right? When you pop the corn, it actually turns into a different substance, right? Browning the fruit of an apple, cut into wedges, left exposed to air. It's kind of like rusting a nail. Okay, that's a chemical change also. That's your only physical change on the list. Alrighty, number 2. A sample of pure water underwent vaporization. Which of the following figures best represents the scenario during the phase change when half the water exists as a liquid and half as a vapor? Okay, so we are in the middle of vaporizing our water, okay, of boiling our water. Half of it is vapor, half of it is liquid. Here's the pictures. All right. Sorry, I gotta move this thing. All right. Greater than 100 C, greater than 100 C, those are not true. 160 degrees C vapor, 100 degrees C liquid. Those are both true. Okay, those are true. Okay, these molecules are further apart in the vapor phase than the liquid phase, so that one is true, which is the third image. Okay, all right, go down here and circle the third image. Let me explain. When you're in the process of boiling something, all of the material stays at the same temperature at the boiling point until all of it has gone from a liquid to a vapor. You can't heat the vapor up greater than 100 degrees C until you have boiled all the liquid water and it has all become a vapor. Then you can start heating the vapor. Okay? That's just how it works. Okay? It's called the heat of vaporization. So they're both at 100 degrees C. Gas molecules are further apart than liquid molecules. Okay, so this one is true. That one is not. All right, question number 3. Which of the following is the best example of a chemical change? And I'm sorry, the way I printed these out, I didn't try a whole lot to try to format these. I just printed them off the thing. So there's 3 examples here and one on the other page. Let's see if any of these is a chemical change. Oh, hey, if you burn anything, it's a chemical change. Burning of wood is a chemical change. Okay, if you heat a copper wire up and it glows, physical change. You just made it hot. Dissolution of sugar in water. Okay, physical change. It has not changed into a different substance. Okay, the sugar does not react with the water. It just dissolves in it. And the last one says, way up here, melting of ice. Okay, again, physical change. You're just changing the phase. Number 4, suppose 100 grams of pure substance undergoes a phase change. So we're like, changing from a solid to a liquid, liquid to a gas, or gas to a plasma. The mass of the substance after the phase change is complete will also be 100 grams. Okay, it has to stay the same. Law of conservation of mass. Chemical reactions, physical reactions, mass is conserved. All right. Dealing with conservation of mass, look at question number 5. Consider the chemical reaction X makes Y plus Z. If 58 grams of X reacted completely, it would be best to conclude that the combined mass of Y and Z formed was, okay, so 58 grams on this side of the arrow, there has to be 58 grams on this side of the arrow. The combined mass means it's also equal to 58 grams. Law of conservation of mass. All right, that was simple. Number 6, we've got part of it right here, and then part on the other page. Which of the following is the best example of a chemical change? Let's look at our solution or options on the next page. All right, we're looking for a chemical change. Liquid water freezing to a solid. That's a physical change. Melting wax candles in an oven. Physical change. Okay, you're just melting it, making it soft, going from a solid to a liquid. Rusting of iron when exposed to weathering. That is a chemical change. Okay, when you create rust, you're actually reacting the iron metal with oxygen in the air and creating iron oxide. That is a chemical change. Okay, tearing a little piece of paper into smaller pieces, that's just a physical change. Question number 7, which of the following occurrences best represents a physical change? Rotting of an egg, that's a chemical change. All right, you're creating hydrogen sulfide, it's a stinky gas. Baking of bread in an oven, that is actually a chemical change also. Okay, the yeast is doing some funky stuff. Burning of gasoline in an engine, definitely a chemical change. Anytime you burn something. Sawing through a wood 2x4, all I'm doing is breaking that 2x4 into smaller pieces, right? That's a physical change. Dun-dun-dun. Moving on. Question number 8. Consider the chemical reaction X breaks down into Y plus Z. If 100 grams of X reacted completely and 40 grams of Y were produced, how many grams of Z were produced? Once again, it's the law of conservation of mass. Okay, X breaks down into Y plus Z. If we had 100 grams of this stuff, right, you can basically draw a line there. This side has to be equal to that side. Now, in this case, we are also given 40 grams of Y. Okay, so what does Z have to equal? 60 grams. All right, 60 grams of Z. It is not impossible to tell. There's your answer. Moving on. All right, question number 9. Consider the chemical reaction X breaks down into Y and Z. If X reacted completely and 70 grams of Y are produced along with 55 grams of Z, how many grams of X were used in the reaction? Okay, it might help you to draw this, right, or write it down again. All right, draw a line there and put the number of grams of each substance underneath its thing, right? 70 grams of Y, 70 grams. 55 grams of Z, okay? What's X? 70 plus 55 is 125 grams of X. Boom. All right, that was easy. Okay, if you heat up a solid without melting it, what happens to the particles? Okay, anytime you add energy, you're adding thermal energy, you're increasing the temperature, the particles are going to move faster and they're going to move further apart. Okay, even if it stays as a solid. That's why you have, that's how a mercury thermometer works, even though mercury in a thermometer is a liquid. That's why concrete expands when it heats up. That's why metal, railroad ties expand, or railroad rails expand when they heat up. Okay, Particles move faster and they move further apart. So they spread apart, move faster. That sounds good. All right, that's the correct answer right there. All right, guys, that is D1 through 4. We are on to D5, and we're 10 minutes in. You know what? I'm going to stop and make this one its own separate video. All right, here we go.